Okay, today we are discussing the derivatives of trig functions. And so you have a worksheet to go with this. And so before we get right into the derivatives, we're going to recall a little bit about trigonometry. And so we're going to first graph the sine wave. And so if we have the sine function, how you graph a trig function generally is you divide it up into the four main points where it's an x-intercept or a max or a min. And so if you recall, sine has a period of 2 pi, and you usually take the period and divide it by 4 to get those important places. So 2 pi divided by 4 is pi over 2. And so I have divided up my axis by pi over 2 spacing. Okay, and so by the time I get to 2 pi, I'll have one complete period, and I've decided to go another one so I could see two periods of the sine wave. Okay, so if you learned the unit circle or special triangles, then this kind of helps you know what the sine is. If you remember these points, this is 0, this is pi over 2, this is pi, this is 3 pi over 2. So the sine of an angle, if you're looking at the unit circle, is the y coordinate. So this point on the unit circle is 1, 0. So we'd say, okay, the sine of 0 radians is the y coordinate, which is 0. And the cosine of 0 is 1, which is the x coordinate. And so right here at pi over 2, this is the point 0, 1. This is the point -1, 0. This is the point 0, -1. So this is true this is just the unit circle truth. But if we wanted to call out a sine value of an angle, you would look at the y coordinate, or if you want to look at the cosine of an angle, you would look at the x coordinate. So right here, the sine of 0 is 0. So we're right here. And the sine of pi over 2 is 1. So we're up here at 1. And so the sine of pi is the y coordinate, which is 0. And the sine of 3 pi over 2 is the y coordinate, which is -1, down here. And then the sine of 2 pi, we've cycled all the way back here to 0. This is a coterminal angle. The sine is, again, we're back here at 0. So this is one period of the sine wave, and then this would continue. We go high, middle, low, middle, and this would be a second period. That's the sine wave. While we're at it, let's just go ahead and graph the cosine, because we want to have that guy on there too. So the cosine is where you look at the x value. So the period of cosine is also 2 pi. You would take the period and divide it by 4 to get those x-intercepts and the maxes and mins. The amplitude of the cosine is the same as it is for sine. It goes between 1 and -1 when there's no vertical stretches or anything. And so let's just graph a cosine wave at 0, at the angle 0. The cosine is 1, so it starts up high. I think I made my 1 too high. It starts high, and then at pi over 2, the cosine is 0, and at pi, it's -1, and at 3 pi over 2, it's 0, and then at 2 pi, we've cycled, and we're back up here to 1. And so this is one period of a cosine wave, and it would continue with this pattern. Middle, low, middle, high, middle, low, middle, high, and so on. There's a cosine wave. Okay. Now, we want to look at we're headed towards looking at the derivative of this, but what we've come off of is being able to look at the graph of a function and try to map or graph the derivative of that function. So that's how we're going to begin to do this. So let's look at the sine wave right here. Okay, where we're going to a maximum point in turning around, think of it as the tangent of the slope of the tangent line. So the slope of the tangent line at a turning point, it's increasing and then it begins to decrease. The slope of the point right here is flat. The slope is 0. And the slope right here at this turning point is 0. And the slope right here is 0, and here is 0. So if we're going to map the derivative, we're mapping or graphing the slopes of this curve. So right here at pi over 2, it's 0. And right here at 3 pi over 2, it's 0. And right here at 5 pi over 2, it's 0, and at 7 pi over 2, it's 0. That's what we've discovered by looking at that. Now, if we're thinking of the slopes right here, this is increasing, so it's positive right here. So the slope would be positive right here. And then between this 0 and this 0, it's decreasing. The slope of this tangent line is negative. It's negative all through here. And then from this 0 to this 0, we're going up, so the slope is positive here. And from here to here, it's negative, and from here to here, it's positive. Let's see if we can try to map that. Between 0 and pi over 2, it's positive, okay. And then it starts high, and then it's still positive, but it's getting a lower, it's a smaller positive until it gets to 0. So it starts here, and then it gets smaller until it gets to 0. And then it goes negative between here. And so it turns out that it kind of goes like this. And then it's positive, and then it decreases and goes back to 0. So it increases, and then it goes back to 0. And then it decreases, and then it gets less negative and gets to 0. So it decreases and gets less negative till it gets to 0. And then it goes positive again. So it kind of looks like that if you were to map this derivative. So if we're just looking at this curve and saying, hey, what does that look like? Does that look like anything that I've seen before? You notice that it sort of looks like this graph right there. So you might have a suspicion, hey, is the derivative of sine, is this maybe equal to the cosine of x? We're going to look at that and see. Let's do the same thing with this cosine wave. So what do we think this might look like? So right here, at the top right here, this is a turning point. This is, because we know what the cosine wave, we know that's a turning point. So we know that that slope is 0 right there. It's horizontal. This is horizontal. This is horizontal. This is horizontal. This is horizontal. So let's go ahead and mark those zeros on the derivative graph. Right here at 0, it is a horizontal tangent, so we say that's 0. Right here at pi, it's 0. Right here at 2 pi, it's 0. Right here at 3 pi, it's 0, and then right here at 4 pi is 0. So we found the x-intercepts where the slope is 0. All right, let's say what's happening between 0 and pi, it's going down, the slope is negative. And how's it going negative? Well, it's a little bit negative, more negative, and then close to 0. So what's happening here, it gets more negative, and then it slows and gets close to 0 again. And then what's happening between pi and 2 pi? Well, it turns positive, more positive, and then less. The slope starts to taper off towards 0. So it's kind of doing this sort of thing. And then it's going to do the same thing like that. And so if you look at this graph, you're like, hey, that kind of looks like a trig function. Is it sine? And you're like, well, no, it's not sine, but it sort of looks like a version of sine. And so if we were to take the sine wave and maybe put a negative in front of it, it would reflect it across the x-axis. Then this part would be down here, and this part would be up here, and this part would be down, and this part would be up. And that's what that would look like. So we might just suspect, does the derivative of cosine equal to negative of the sine of x? This is what we suspect. And so let's just look at something. In math, if you want to know for sure, you always go back to the definition of how it's defined. So we're about to do that. We suspect maybe, that the function sine x, his derivative is the cosine of x. And we suspect that maybe the function cosine of x, his derivative is, I don't know why I made them male today, but I'm calling them hims. The derivative of cosine is negative sine of x. That's what we're thinking that might be true. So let's go back to the derivative, the definition of the derivative, and it's this right here. This is one of the definitions. So let's have a look at this guy. Okay, so the limit, we say f prime of x in general is the limit as h approaches 0 of f of x plus h minus f of x all over h. So before we use this for one of our sine functions, there's a couple of things that we need to know. I'm just going to go ahead and tell you. It's on your worksheet, but it's this, that if you have the limit of some angle as it's headed to 0, of the cosine of that angle minus 1 divided by that angle, this is equal to 0. You can prove this by a table function. You can look at a table of values and watch it approach. And this, if you put this in your calculator and you take from the left of 0, from the right of 0, and get closer and closer and closer, you're going to see that this goes to 0. Here is the second thing we need to know, is that the limit as theta goes to 0 of the sine of theta divided by theta, this limit approaches 1. Again, you could use a table of values in your calculator to show that this is true. So before we head into this, we are saying, given that this is true, that this is true, show that, or determine f prime, determine the derivative, d, the derivative with respect to x of sine x. Let's figure out what this is. All right, so let's take this. Well, let's go by the definition. So first we'll take f of x, which is just, f of x is sine x in this case. So just so we're clear, sine x. And what we're trying to find is f prime of x, which is the derivative of the sine of x. That's what we're trying to do. Okay, so we'll use this, the limit as h approaches 0 of f of x plus h, or the sine of x plus h, minus f of x, the sine of x, all over h. Okay, this is what we have to evaluate, and whatever we get here, this is what the derivative of the sine equals to. Well, to do this, we have to recall a little bit of trig, and that is the sum of angles. So there is an identity that you were introduced to when you took trig, and it's this. It's that the sine of x plus y is equal to the sine of x times the cosine of y plus the cosine of x times the sine of y. Now, when I taught trig, I didn't make my students memorize that, but we used it an awful lot. So be able to come up with this and say, oh yeah, I've seen that before. So let's apply that here. So this is going to be the limit as h approaches 0 of the sine of x times the cosine of h plus the cosine of x times the sine of h minus the sine of x all over h. Okay, what can we do with that? Well, I see two sine x's. I'm going to factor that out. This is the limit as h goes to 0 of the sine of x times the cosine of h minus 1 plus the cosine of x times the sine of h all over h. Okay, very good. Now what I can do here is I can split this into two. Limit law says I can split this into two limits, so I'm going to do that. I'm going to say this is the limit as h goes to 0 of this, plus the limit as h goes to 0 of this. Okay, what can I do with that? Well, look at this sine x. There's no h in that. I'm not supposed to replace x with anything because this limit is written in terms of h. This is not going to have any effect on the limit. It's like a constant almost. So I can take the sine of x and move it out in front of the limit and just concentrate on the limit by itself. So I can say this is equal to the sine of x times the limit as h approaches 0 of the cosine of h minus 1 over h. Over here, this cosine of x is not anything to do with the limit as h goes to 0. It will be unaffected, so it's almost like a constant. So I'm gonna pull the cosine of x out in front and then say this is the limit as h goes to 0. Limit laws allow me to do this, of the sine of h over h. So now, let's borrow this given information. The limit as theta goes to 0 of the cosine of theta minus 1 over theta is 0. If I replace my h with thetas, I can say that this value right here is 0. So what I'm looking at by this is what I'm using. This truth right here, right? I'm applying that truth right here and saying this is a 0. So I'm saying this is really the sine of x times 0. plus the cosine of x. And now I'm going to look at this. The limit as theta goes to 0 of sine of theta over theta. The limit as h goes to 0 of sine of h over h. These are same thing. So I'm going to apply this information right here. I'm going to say this is really a 1 times a 1. So this is the sine of x times 0. Anything times 0 is 0, plus the cosine of x times 1. We find that the derivative of the sine of x is cosine of x. That is by definition. We could go through and do the same thing for cosine, but I'll just go ahead and tell you the ending. It is actually negative sine of x. And so we're gonna just say this is truth, it is truth, and you could prove it to yourself by going through the definition for cosine just like I did for sine. We're gonna do 2 more examples, I think, maybe 3 more on this video, and then I'll stop and we'll do a second video on the same topic. Okay, what I want to do next before we leave this is let's figure out what the derivative of tangent of x is. So let's see, we've got these 2 established. Now these are things that you will need to commit to memory if you do not put this in your memory. And there is, of course, ways to halfway do this class. I totally do not recommend that, because when you hit count 2, you fail. So I want you to memorize this. Make this just really quick. You're going to have to, there's going to be a table of functions. You want to know them by heart. So even though this is online and there's all kinds of ways to get around things, you will really be doing yourself a disservice if you don't just go ahead and memorize it, because it's just the truth. Okay, what's coming next is I want us to figure out what is the derivative of the tangent of x. Okay, this is kind of cool because you guys already know enough to be able to figure this out. Given this information, we can figure out what the tangent of x. So what is the derivative of the tangent of x? Or what is the derivative of the sine of x over the cosine of x, because that's what the tangent is. Well, we can figure that out because this is a quotient and we can apply the quotient rule. So before we do this, there's just a little bit of trig you want to recall, and that's the Pythagorean identities. And they go like this. Sine squared of x plus cosine squared of x is equal to 1. These are the other ones you want to remember. Sine divided by sine is 1. Cosine divided by sine is the cotangent squared of x. 1 divided by sine is the cosecant squared of x. Do you see? I never really memorized those, which maybe I should, but I can write those down very easily by, you can take this one, which I did memorize, and divide it both sides by sine squared of x. I'm going to go through and divide both sides of this by cosine squared of x to get the other Pythagorean. Sine squared divided by cosine squared is the tangent squared of x. Cosine by cosine is 1. 1 over cosine is the secant. Oops, that's an equal sign. Is equal to the secant squared of x. So I was able to come up with the Pythagorean identities by just doing a little bit of algebra. And you've seen those before. So now, here's the task before us. We're going to take the derivative of tangent of x by applying the quotient rule, which we learned in 3.2. So, low d high minus high d low over low low is how you do a quotient. So, this derivative will be low, cosine of x, times the derivative of the high. The derivative of sine is cosine of x, minus high sine of x. D low, derivative of low, is negative sine x, all over low low. Cosine of x times the cosine of x is the cosine squared of x. Right here, I just want to take a moment to make sure everybody is clear on this, that when I write this, the cosine squared of x, this is equal to the cosine of x squared. This is not equal to the cosine of 2x. That's a double angle. This is something totally different. So just be careful with that notation right there. Okay, what can we do with this? We can say, okay, well, this is cosine times cosine is cosine squared. Negative times negative is a positive. Sine times sine is sine squared over cosine squared of x. But this looks very much like this, and this is a Pythagorean identity, and so that's a 1 up there, is 1 over the cosine squared of x, which is otherwise known as the secant squared of x. Turns out that the derivative of tangent of x is the secant squared of x. All right, Now, one of your homework problems is to do what I just did for a different trig function. Apply a quotient rule and figure out what the derivative is. But for now, just so we can go ahead and practice doing some derivative stuff, I'm going to tell you what the rest of this chart is. Again, you should commit this to memory. And if you do homework problems, you can't help but commit it to memory. So here we go. What are the other functions we're going to be looking at? Here is another one. What is the derivative of, we want to know cotangent, secant, and cosecant. So that's what we want to look at. Okay, so the derivative of the cotangent of x, the secant of x, and the cosecant of x. All right. The derivative of the cotangent of x is negative cosecant squared of x. The derivative of secant of x is secant x times the tangent of x. The derivative of cosecant is negative cosecant x times the cotangent of x. That is what they are. Here's just something to sort of pick up on. When you see the co or a co function, cosine, cotangent, cosecant, the derivative has a negative involved every time. The other ones don't. That's just something to help you through. All right, I'm going to do example 2 from your book, and this is what I put on your sheet, and it says, differentiate the function f of x equals to this. For what values of x does the graph of f have a horizontal tangent? So let's figure this one out. F of x is equal to the secant of x divided by 1 plus tangent of x. F of x is the secant of x divided by 1 plus tangent of x. All right. All right, let's do this one. Okay. So the instructions say differentiate this. Find its derivative. Okay. And then figure out for what values of x does the graph have a horizontal, this graph have a horizontal tangent. Okay, so let's go ahead and take its derivative. F prime of x. This is quotient. I'll use quotient rule, is low. Derivative of high. Derivative of secant is secant tangent. Low, d high minus secant of x. D low, the derivative of 1 is 0. Derivative of tangent is secant squared x. All over low, 1 plus the tangent of x squared. Okay, so let us work on this. What can I do with this? I can multiply this out. That would be secant x, tangent x. 1 times this is secant x, tangent x, plus secant x, tangent squared x, minus secant to the third x. Okay, what can I do with that? Let me think for a second. I'm going to look at my Pythagorean identities and say, is there something I can do with this? Let me factor out a secant from these two and see what happens. The secant, and this is all over 1 plus the tangent of x squared. I just want to see if I can simplify it just a little bit. Let's see. Let me think for a second. I want to apply this somehow. If I could get secant, then that would be tangent squared minus secant squared. Oh, let's do that. I'm going to factor out 1 secant from these two and see what happens. So let's see. Secant of x, tangent of x, plus I'm going to factor out a secant, leaving me with tangent squared of x minus secant squared of x all over 1 plus the tangent of x squared. So I found the derivative. Right now I'm just kind of simplifying it. Tangent squared of x minus secant squared of x. If you look at this Pythagorean identity, if I were to subtract secant squared, and subtract 1. This is equal to -1. Tangent squared minus secant squared is equal to -1. So I'm going to replace this right here with a -1. So I find that what I get here is, if I now I'm going to factor out a secant of x. So if I take a secant of x out, that leaves me with tangent x minus 1. Tangent of x minus 1. And all of this is over 1 plus the tangent of x squared. Okay, now, what are we going to do? We're going to answer the second question. The second question says, second part says, for what values of x does the graph of f have a horizontal? Well, this graph right here is going to have a horizontal tangent. If you recall the sine wave and the cosine wave, right at the turning point, it's increasing and then it goes down. This little point, the turning point, is where it stops to be a 0. Negative turns positive right here is where it's got a horizontal, horizontal, horizontal tangent line. And so that means the slope at a horizontal is 0. So f prime of x is the slope of a tangent line. So basically we have to answer when would this equal to 0 to say when we'll have a horizontal tangent. A fraction will only ever equal to 0 when the numerator is 0. The denominator may never be 0, that's division by 0, but it only ever equals 0 when the numerator is 0. So basically, we have to answer this question. When does the secant of x times tangent of x minus 1 equal to 0? This is already factored, so when does the secant of x equal to 0? And when does the tangent of x minus 1 equal to 0? That's what we have to solve. All right. Well, let's think about the secant graph. You can verify this with your calculator by plugging in values. But if you think about the secant graph, it is built off of the cosine graph. This is the cosine. The secant graph looks like this. Right? Do you remember that? So when will the secant equal to 0? The 0 is in this part. The range of secant, the range is -infinity to -1. 1 to infinity. So the secant will never, ever, ever equal 0. It's undefined there. So this produces no answers. So now we're down to this. When will the tangent of x equal to 1? So if you recall your unit circle, the tangent of x equals to 1 when the cosine and the sine are the same value. And that happens at pi over 4. And also at positive 3, no, 5 pi over 4. Oh, come on. 5 pi over 4. So, because in quadrant 1, it's positive over positive, and in quadrant 3, it's negative over negative. But in quadrant 2, the tangent of the 3 pi over 4 is -1, 7 pi over 4 is -1. So, it's going to be at pi over 4 and 5 pi over 4. So, how you can write this succinctly is when x is pi over 4 plus n pi, and that will catch all of the values when the slope of the tangent line is 0. All right, that is all we're going to do on this first video. The second one, we're going to practice doing derivative stuff.